morning, everybody. Can everybody hear me? Yes. Wonderful. Thank you. Well, first of all, welcome to our side event. We have a very special topic today. It's on quantum technology, a topic that's quite unique, but will become more relevant in the next decades. When I learned last year that the United Nations has declared 2022 the year of the quantum technology, I was very excited and I immediately contacted the CSTD because we have just launched an initiative on this topic. So I will briefly introduce our organization to you, and then our two experts will show you a presentation in an interactive dialogue. And at the end, I hope that we'll still have time so you can ask us questions. And we make a short round of Q&A. So the Diplomatic Council is a unique organization with ECOSOC status, combining a global think tank, a world-leading business network, and a charitable foundation. Our members gain access to a global network of leaders from the highest levels of diplomacy, business, and social change. Through our numerous forums, programs, and initiatives, our experts share their experience and expertise to facilitate education and knowledge transfer, driving humanity forward. It is in this context that the Diplomatic Council has established the Diplomatic Council Quantum Leap Initiative. We have launched this initiative to raise awareness of how quantum technology can be used for the benefit of humanity. So in the next 50 minutes, we will explore the utilization of quantum technology to enhance the quality of life for all people in the world, in particular for the less privileged one. So the key areas that we will focus on in our presentation is climate research, medical technology, material science, artificial intelligence. We will prepare for the quantum crisis, quantum cloud computing, so that means quantum as a service. And the objective of our event is to prepare governmental, societal, and economic stakeholders for the immense opportunities and challenges posed by quantum technology. It will highlight the various fields likely to be transformed by this new technology and outline the expected nature of these changes. In doing so, it will lay the groundwork for potential discussions within the United Nations and its member states on necessary and meaningful governance and monitoring programs. I am very pleased to introduce to you our two absolute experts in the field of quantum technology. This is Harald Summa. He's a German internet pioneer and entrepreneur. He has founded the ECHO Association. This is the internet industry in Germany, and it's based in Germany, founded in Germany, and meanwhile it has over 1,100 members, and it's the largest association of the internet industry in Europe. Matthias Reidans is from the company Rosenberger, which is specialized on the data center consolidation, transformation projects, and is investigating the innovative potential of quantum technology for the data business. And now we are very excited to share our expertise and knowledge with you and invite you to listen to our experts. Please.
Thank you, Hang. So can you hear me? Welcome, all of you, to celebrate 100 years of quantum mechanics. It's a great honor and pleasure to be here with you and exploring the powerful patterns, topics, and future devices driven by quantum technology. And we'll see which impact this may have on humanity. So let's start with just a view on what the development of technology has done in the past, developing patterns and what now from a candle to light bulb to laser, this technology is, and related to quantum, we are now in a new age and a new era for humanity. Celebrating 100 years of quantum mechanics is because of the foundation was done in 1925. And all of this started to get attention of the public with a finding by Richard Feynman in 1981, where he proposed that we could use atoms, electrons, photons to calculate, to get rid of transistor-based processing and do calculations, creating computers on the atomic and subatomic level. And this was a starting point, creating a new technology for driving with quantum compute to a level which was never expected before to get in reality. So with these physicists, the foundation of the quantum compute started with quantum mechanics. So we had Albert Einstein, Max Planck, Max Born, Pascal Jordan, Werner Heisenberg. All of these, Erwin Schrödinger, founded the principles which now can be deployed into this technology. And this technology has got a lot of facets and areas which we will now explain to you. So this was kind of the first quantum mechanics revolution. And the second quantum revolution then started in the 70s and 80s with findings where experimental evidence was done and achieved to showing that entanglement, the relation, the connection between individual particles, that entanglement is a real thing, and this can be used for engineering purposes, to improve techniques which were already in place, but now get into an entirely new level of capabilities and potential. This, for instance, with Anton Zeilinger, John F. Clauser, and Alan Aspect was in 2022, resulted in the Nobel Prize Award, showing this entanglement is functional, can be used. And the next future evolvement in quantum computing, the third quantum revolution, is visible already at the horizon, because there were findings in the late 90s about behavior of black holes. There were some evidences that maybe entanglement is a principle working in black holes, so that black holes maybe are connected to other black holes by entanglement. And this is an entirely new pattern which will evolve now and will, in theoretical physics, create much more findings. And nobody knows already what this third quantum revolution will bring. So these are the scientific papers published, and our recommendation is just monitor and watch this third quantum revolution. So the United Nations decided to found this year of quantum, which is the year 2025. And there was a huge opening ceremony in Paris, and the public was addressed by, for instance, Sir Peter Knight. We need all of you to change the world by use of quantum technology. If we look in the entire world, the governmental investments in quantum technology is really, really huge. So there are figures which are significant and which are increasing from year to year. There are a lot of startup companies driving new business with quantum technology. You see here the proportion, the ratio, which startups take stake and where's the important business to be expected. So a lot of companies are dealing currently with the hardware components because the hardware is not ready, not yet in the shape you can use on everyday purpose, a quantum computer. So this is really a huge topic where hardware component companies can thrive. Software companies and quantum sensing, quantum communication, this is all evolving currently. And the market potential was investigated by, for instance, McKinsey in a Tech Monitor publishing in July 2024. And you see the huge potential. It's even almost like the AI level. And even conservative figures show significant amount of business. Worldwide research is ongoing. Universities are investing in skills and labs. So all over the world, we have quantum science competence centers. And these are very often the initiation for startup companies. Yeah? So there are a lot of spin-off companies coming from universities like in Maryland and Washington and the TU München. So a lot of universities driving their business by using spin-off companies and creating quantum computers. And not only quantum computers, but quantum computing is the one part where media is talking about because quantum computers are a threat to data security. You may have heard this already, that our public key encryption infrastructure is threatened by the powerful quantum computers breaking the algorithms currently used in encryption. So it's a huge part to get the data protection level to a new and better state, so that we are again then protected after the quantum compute power is capable of doing this. So the areas are quantum computing, quantum communication, quantum networks, quantum sensing, and quantum application and science, where the AI part, for instance, is. So there are a lot of quantum misunderstandings. Maybe you have heard about this mystic game of quantum. Even Albert Einstein was an opponent of quantum mechanics in the past. And so there's a lot of expectation quantum will not fulfill. You cannot use entanglement for transferring information from one point to the other. You can just create a protected line, but you cannot use this as a transmission line to transport information, for instance. And the superposition, so that the quantum mechanics principles are used, are not that kind of magic or crazy, or it's really a physical fact that particles can be entangled, and this can be used for creating quantum technology devices. So how is all this done? The compute unit of a quantum computer is called qubit. Ever heard qubit as a term? Yes? Okay, so it's entirely different to the CPU-based, the transistor-based processing. The qubit can have several levels, several states simultaneously at the same time. And this can be used to calculate in an entirely different way. So that's why with qubits processing, you need to create absolutely from the scratch new software development kits, new programming languages. So anything you have about digital programming learned is past. is an entirely new sphere. It's more or less analog computing. And Harald?
Matthias gave me a nice picture for that. Take a record player and a record where you can listen to the music, and at any stage you can hear all the orchestra members. On the other side you have a CD-ROM where you have a digital flow. So the one is digital, the record is analog, and we are in an analog world.
Thank you, Harald. Great metaphor. Yeah. Truly, the analog is much more powerful than the digital because you need not to rely on just two states. You have simultaneously a lot of levels, and that's why it's much more complex to create a programming language which is capable. And the challenge is to build up then processes and coding which works on these quantum computers. The hardware issue is with the quantum computers that these qubits are not very stable. They are volatile, they are not precise. So if you ask a quantum computer, add 2 plus 2, what is the result? Nearby 4. Nearby 4. But it will never be 4. That's why you need kind of a glass, yeah, to precise the view of the quantum system to a definite result. And that's why you need much more physical qubits than logical. That's why you need to have from, for instance, 1,000 qubits, 990 just to correct the errors of the 10 qubits you need to use. Yeah, so you need really a large amount of hardware which is driving these qubits in a way that it's like a common, reliable computer we all use in everyday life. Yeah? So this is really a challenge to have a scalable and precise and stable system with qubits. There are several architectures in the last decades created by the engineers, so you can use trapped ions creating these qubits, or you use a diamond, yeah, the carbon dioxide grid in a diamond, to get these qubits fixed in a way that they would not be kind of volatile, that they disperse. And there are spin qubits as well existing, neutral atoms. This is done by laser technology, yeah, to get these atoms fixed and use these as qubits. Superconducting, this is the one most of you may have seen in the media, these large dilution refrigerators, 3 meters high. Yeah? And the QPU, the processing unit of the quantum computer, is just a fingernail. But you need this dilution refrigerator, 3 meters high. You see this? 3 meters high, just to cool down to a millikelvin temperature this QPU. So it's still done the calculation on the subatomic and atomic level, and you need a surrounding environment of engineered stuff to make this work. And all of these have different capabilities and different purposes. So the next sphere is communication with quantum. You can use this entanglement to protect communication lines, to make communication transmission from A to B absolutely secure, so that no one is able to intercept this. And this is entirely new. Never in history it was possible by engineering to protect a communication line 100%. This is the first time. And this is absolutely disruptive. And maybe Harald, yeah, as founder of internet connections, yeah, is really appreciating this, that his lines are not compromised. There's no way to intercept. So the quantum has got two sides of the medal. Yeah? The advantage is we can protect the lines. The disadvantage, the quantum computers are capable of breaking the encryption. So it's two sides of the medal. Yeah? We have advantages, disadvantages. And the quantum communication network are even possible to get into space and protect communication lines between continents. So this was done, for instance, 2017 in China with a video conference established between Shanghai and Vienna successfully, so that there was no interception possible. And this is the future of communication and the future of the internet, and maybe the quantum internet is a metaphor as well. And maybe Harald, as a founder of the internet in the last decades, has got more a vision of the quantum internet than me. So maybe, Harald, you would explain what you think about the quantum internet will evolve.
Yeah, if we think about communications nowadays, there's the internet, of course, nothing else. There's nothing left. And if we think of securing this, because the internet is not a secure place, it is clear that these new technologies will find their way into communications. So what is the problem? If we have nowadays communications between 2 points, A and B, on a fixed line, of course the technology, the entanglement is easy to install. But the problem is that the longer the distance between A and B becomes, the more difficult will it be to secure the state. So if we think of internet, we have the problem that we have not just one line, A to B, but we have several hops between the instance. And we have to find a way that we amplify the signal over several routers, as we do it today. So what we need in the future is a quantum repeater that takes the signal, passes it on to the next step. And this is where the most of the research is done now, to find devices that are small enough and cheap enough to be used in these communications. Today, you have to have a small repeater or an amplifier every 30 to 70 kilometers in order to bring a signal from A to B. So there are tests that show that it is possible to connect, for instance, Geneva with Bern or with Zurich, but it is very expensive because every 30 kilometer you have to install such a huge box that is almost half a room full of equipment to get the signal passed on. So what we envisage is that in the next 5 to 10 years, these huge devices will be shrink into a small plug, something like this. This is let's say, the amplifier for the quantum communication. But this will take time.
Thank you, Harald. Yes, this is a challenge for the engineers, of course, to make the devices which carry on this QKD, quantum key distribution, from this size box to this transceiver. So it will take, I don't know, a decade maybe. But then it will be really a standard of making internet communication much more secure than currently. And in metro networks, for instance, in New York or in London, in Berlin, in Munich, and in Seoul, in Korea, there are these test beds already working, they are stable, and they will be connected then to other metro networks. And this is just the evolving structure of the future internet. So the next topic is quantum sensing, that you can have with quantum parts, components like qubits, a much more sensitive technique than it was possible in the past. So you can optimize microscopes, you can have a magnetic field sensing, you can have a gravitational field sensing, you can have much more precise timekeeping of systems. So quantum sensing is really, really a huge part of engineering and will really, really change our everyday life. Yeah. So that quantum sensors are built in devices you use on a daily basis, in cars for navigate, in any kind of possible gadget, yeah, in watches and so on. And it's for research as well very important. So you will have a conjunction between quantum compute power, quantum sensing, and software. So the quantum AI conjunction. For instance, Google, one of the large companies in the world, as they were driving into this business, they created a department, it's Google AI Quantum. It's not separated between AI and quantum. It's just one department. Yeah. And so these are areas where a lot of benefits will be handed over then in the future to a lot of us. So machine learning is going to be optimized with quantum compute power, and optimization is possible.
If you start developing a large language model today, to train the model, it takes weeks, hundreds of thousands of processes to get the model done. Imagine that with quantum computers, it might be in a second or 10 seconds. Neural networks figured out in this technology are very fast and not much more or less power consuming than processors of today. So I think the combination of AI technologies and the compute with quantum computers will bring another push into AI applications.
Yeah. Thank you, Harald. That's why we need a new programming base, to create all of these patterns, to use this as applications. And there are SDKs around hundreds, thousands of programmers worldwide are working on these and on optimization of these SDKs. So companies create already algorithms which are useful, and the evidence is already shown that these are working, even though qubits are not scalable, not precise enough. But even currently, it's possible to see what optimization of, for instance, analyze of business risk is resulting in. And the quantum machine learning is optimizing all machine learning patterns. Yeah, so you can rely on a system which is capable of a level of achievement which was never possible before. And these really is resulting in new companies driving new applications based on these quantum programming. In summary, the enormous potential. There are, of course, some downturns, disadvantages, risks, so we need to raise ethical questions. All of these parts can be used for the good, but some can be used for the bad. And that's why we're here to talk about, for instance, the SDGs. So we found in analyzing the SDGs, 6 out of the 17 SDGs which are really impacted by quantum technology and can improve significantly. Climate research, optimizing urban infrastructures, logistics, getting more safety in power grids for cities, and so on and so on. Securing communication. So there are a lot of areas impacted, and the SDGs as well. But when you have an evolved technology, at the point you are not able to see all the consequences, you would nevertheless be required to act now. So the problem is, if we don't see what at the end this will bring, what is the call for action now? So it's really a problem. It's called the Collin-Rich dilemma, yeah, that you almost need to act now, but you are never able to see the expectation in which way this will evolve in the next decade. So which steps, which action we need to do now for taking care of this downturn of the technology as well. So the good and the bad. What is with the data security topic, the geopolitical risks, economic disruption could be the consequence. And the access to systems maybe is compromised by these systems. So we've seen, for instance, in the Ukraine war, what just within 3 years happened on the battlefield. The entire technology used was revolutionized. Of course, in the bad way, and for creating a lot of suffering and bad things. So bare pain triggers disruptiveness, and this is really a fact. And that's why it's really a true story. Quantum warfare will be as well a pattern we need to deal with. So this is more or less the downturn. Yeah, we need to really take care about the ethical impacts of this technology. That's why a lot of recommendations are currently developed and created. Think tanks like here, our organization, you all can contribute to answer these ethical questions, these ethical problems. And we need to go with a deep dive into technology assessments about all of these. So the recommendation is we need to take care at first about our data security, because maybe it's really a huge threat for the global infrastructure, the world finance system, the critical infrastructure of cities, and so on, the nuclear weaponry, for instance. And so in our NGO, we talked a lot about these patterns. What really is the impact for humanity? Will it evolve in a good way? Will it evolve in a way we are not appreciating? So in the past, we have seen genetic engineering has got a lot of downturns. Yeah? Gain of function research, for instance. Yeah, the spread of artificial created diseases. Nuclear technology, proliferation. And quantum now is at the stake to get that we handle this in a responsible way. This ethical roadmap is divided into areas like we can intensify multidisciplinary collaboration and adding regulatory frameworks, creating standards for using quantum technology. Export regulations, for instance, are in place since 2021 that quantum technology components cannot be delivered anywhere in the world, but just to several regulated receiving countries. So the public awareness and transparency need to be improved, and international cooperation in the quantum science and quantum research and quantum technology field is now due. So Harald created this slide to get kind of a conclusion of a summary out of this. So there's a good side, the pro side, and the contra side of this. Maybe Harald, you would go into some of these topics?
Sure. On one side, we have this unbelievable computing power. We can secure communications. We can create new devices for sensing and metrology. This all will increase economic competitiveness, and the scientific advancements will again bring us deeper into the material, deeper in the ideas, and bring out new physics and technological revolutions. The downside, of course, is the cryptography disruption. Quantum computers can break any encrypted information, be it from good guys or bad guys. We have to think about the ethical and geopolitical issues, the risk of militarization, surveillance, and inequity. And we have a very high uncertainty in timeline for the practical use of quantum advantage in the future. So there are still significant technical hurdles and scalability issues to solve. I think that one of the major challenges that we will have is missing educated human resources for that. So a lack of trained personnel and a lot of need for interdisciplinary education and diverse talent pipelines. Finally, also this technology consumes energy and has a lot of environmental cost. So altogether, I think there is a future that is bright, and we should take care of the clouds that may come from the left or the right side.
Yeah. Thank you, Harald. But the powerful quantum computers, and in conjunction with quantum sensing and AI, of course, can create progress in so much fields of society, in so much areas, that all of us deep into this hope, of course, that this good story will prevail and will succeed, and the downturn is handled to get handled. So what is now the recommendation? Let's just take one example. Let's use the quantum safe communication to protect communication lines and driving more control, for instance, for nuclear technology. So this is one possible solution, that system which is currently at stake to be compromised, in proliferation of nuclear weaponry and so on. So that it's possible to create quantum secure communication to achieve a control about nuclear technology items. And this would be kind of a quantum twist to just see that in the past we do have nuclear powers and the new quantum technology, and this now could be shifted to get quantum power into control about nuclear technology. So this, for instance, would be just one sample to create an advantage for the world. So let's summarize just the terms, the call to action, what we need to do now. We need to prepare for the quantum crisis, which is created by this encryption threat. We can monitor the third quantum revolution, the progress, learning about entanglement in black holes. So this is really, really an interesting thing. And maybe in a decade or maybe in a century, this can be used for creating technology as well. Then all of us, all of you can contribute to the quantum advantages and see progress on creating chemical substances by enhanced research, optimizing logistics, and have a lot of achievements with quantum. And all of you can contribute to the progress of this quantum positive things. And join the quantum twist. So think about the way if quantum secure communication could really help us and make the world safer and a better place. And this is our recommendation just after the 100 years foundation of quantum mechanics with 1925 principle of Werner Heisenberg, the uncertainty principle, the base on this quantum mechanics. So after 100 years, we now are at the stage where we can look into the next 100 years. And all of you can contribute to make out of this quantum technology, out of this quantum revolution, really, really a thing everyone can profit and benefit from. So now we want to open the last minutes to Q&A and a discussion. So our summary is at the end. So currently, if you have the possibility to ask questions, then questions.
Does anybody want to make comments or questions?
Comments, questions.
Yeah.
Yes, please.
Thank you. Thank you for a very interesting presentation. I think this is very, I don't know if you can. I have a couple of questions. One question, we know that the science community worldwide is, the more science develops, is it more on elite. So does it mean that this quantum crisis and the requirements, especially in terms of the new algorithm, which you most probably, I think, I was curious what you call the software, but most probably the algorithm will call the software. Does it mean that the requirements for the quantum algorithm requirement for the other fields of science will make the science community even more elite as opposed to now? Does this risk exist?
Yeah.
So that's the first question. And my second question, we were talking about lead lighting, for example, and the everything that it can bring to us. But now we learn that there are quite a lot of danger for the eyes. For example, you can use different lead lighting, but the majority that we are using worldwide are damaging for the eyes. So when you're speaking about the quantum, the hardware, that exists, and spreading across the world, what can be the consequences as you think, because I think it's theoretical now, but are there any thinking about what can be another minus or consequences? Is it called for the nervous system? Is it called for the other things? Is it called for the pressure, whatever?
Yeah. Thank you very much for this question. For the first point, is this creating kind of a new elite, and science is evolving in a more or less uncontrollable way in this quantum field? Is this really a downturn? Of course, there are two parts. Yeah? There are very few scientists working on this, and as long as the results are not spread into our everyday devices, this is not kind of that much visible. So if we see in the past what the science elite was doing and what the results were impacting in our everyday life, yeah, then these elites are not in an entirely different responsibility now just because it's quantum and it's based on quantum mechanics. So the responsibility of a scientist is still the responsibility of a scientist. And is this answering your question?
Yeah, thank you. But I just thought that the community will be even shorter, even squeezed, as opposed to right now.
Yeah. Yeah, it's a good point. Yeah, we need to intense educational initiatives. The second question, that maybe there's a dangerous field with using LEDs, using lasers. I think, Harald, you are more or less the expert in how the internet is from the technology point of view driven. Yeah, the components are not that kind of exotic or not that kind of harmful, so that we really have new protection patterns to spread all over the world. So it's more or less a common laser system, just with some engineered new techniques for handling polarization, for instance. But it's not the case that these lasers used for quantum communication are entirely different. You will not have a entirely different way to handle this technology.
With regards to practical applications, I'm sorry, I'm fine. Your estimation of 5-10 years, we will have, these repetitors, everywhere. A little bit optimistic, because as far as I understand, the current quantum computers or models that we have, that we're searching, first they're in individual, in individual samples, and so how do you see this 5-10 years happening? And actually, as far as I understand, the tasks that current quantum computers can solve, they're extremely basic. So how do you see how these 5-10 years, how will 5-10 years will have repetitives?
Maybe you point at this, what Jensen Huang was in at
because
the.
I don't see this happening. So my concern is that we will be, meeting here in 30 years.
Too far away.
Speaking about 5 years.
Yeah.
So I don't see.
Okay.
Okay.
I'm sorry.
Yeah,
Maybe
no
I'm
problem.
over-pessimistic,
No problem.
but I observed I was active in solar energy, in solar photovoltaics. So I saw
I see.
how it was happening, how long this technological leap was taking place before, from some samples used and extremely expensive used in the space,
Sure.
they came to our life.
Yeah.
I don't see this happening with quantum computers. So my question is, when it will happen? When we can commercialize it?
That's-
be happy and
it's
all
a-
these threats will
It's a very good question. That's why I put up this quantum is now.
Yeah.
You see already the evidence that the software is capable, the sensors are capable, the first qubits stable enough are capable. So you need this entry point, to get into a stage where you can start with engineering, and this is already done now. So you can optimize, for instance, logistic programs for robots. You can improve drug discovery already now with quantum machine learning algorithms, for instance. You can optimize the battery technology for the traffic infrastructure. So this is already at hand now. And what you are pointing at is, of course, what Jensen Huang. Have you seen this on 20th of March? Was Jensen Huang was publishing in an interview at his conference in NVIDIA. He told, the very reliable quantum computer is still 15 to 20 years far. And then the stock market of quantum companies went down. So afterwards, he refused and withdrew and said, okay, this was not exactly the point he aimed at. So he talked about the capability of having a quantum computer, a reliable quantum computer in everyday life, like this smartphone. So this really, I admit, is 15 to 20 years far. But the research institutes, the already existing cloud computing centers, all of the progress which was done on error correction, for instance, last year, this is really, really improving. So there is the reason and the place to be optimistic in this.
I think Gambia had a question.
Yeah.
Yes, thank you, Ambassador Gambia in Geneva. Quite a fascinating insights that you have shared this morning. And you're sharing this in the context of global concerns as it relates to the human rights issues around artificial intelligence and the lack thereof of centric approach to AI. And in your speech, you have raised the same issues. And the larger challenge is this going to further widen the divide between developing countries and the developed world? And how do you see developing countries grappling with not catching up in the digital age and not catching up on the AI, and now exacerbated by the rise of quantum? Quantum is here to stay and is evolving. And it's redefining quantum mechanics, creating new physics, which is moving towards creating new technologies. So I'm wondering your thoughts and insights on the readiness of developing countries and the attached to that is
Yeah.
we are in the process of, well, we've just put together global governance for data. And what role do you see we need to keep in mind as we formulate global governance around data, particularly in the issues of data leakages that may be caused by quantum? And the double-edged sword that you've mentioned as it relates to crypto, the security aspect, quantum secured and quantum unsecured. When this morph into autonomous systems and militarization of devices embedded with quantum,
Yeah.
what is the role of multilateralism in this mix? And also, lastly, the role of universities in terms of building the next generation of physicists and scientists that can be at the cusp of building building responsible quantum in the future.
Yeah, this is a very good question, Mr. Ambassador. Thank you very much. You've seen on the map with the universities that Africa is not a blind spot. So there are a lot of universities in Africa as well working on this, creating quantum centers of excellence and doing research and so on. And so the benefits, for instance, developing better fertilizers, drug discovery and so on, all of this is for countries which are not that kind of developed benefit as well. So it's not only spread to just the already profiting, already gaining countries. It's for all of the countries. It's for all areas of interest. It's for all areas of industries a benefit. So even in the undeveloped countries, they can use this metro networks, quantum safe communication to protect their assets, their treasury. So this is right at hand, and this was never before possible. This is an entirely new technology. Never before it was possible to protect a communication line 100%. And this is at hand for any government, for any country then. So is this answering your question? You're not convinced. I feel you're not convinced.
Thank you so much.
Okay.
Not yet convinced.
All right.
Okay.
I think our time is almost, but maybe one last question.
Yeah. You have started with Max Planck,
Yes.
and you have just answered the question concerning the educational part. Well, Max Planck said that when he was asked about quantum mechanics, how can you understand quantum mechanics? He said that you can't understand, but you get used to it.
Yeah. That's right.
That's my takeaway.
Okay.
The military side.
Yeah.
You haven't talked about the military part. What researches are going on? And well, we know that internet has been developed because of the military.
Yeah.
So, do we have a military side?
Yeah. Maybe you remember the slide with quantum warfare? Yeah. So, of course, there's a military side. Any kind of technology is used for improvements on the battlefield. This will be not different with quantum computers. That's why quantum computers, not only this large dilution refrigerator superconducting systems, you cannot carry them onto the battlefield. That's why it's really currently under development to get these into a transportable way, which is not, which is independent from gravitational impacts and so on. You need not to cool down this. So quantum computers will have their military aspects. It's the case. I cannot avoid this consequence, for sure. But on the other hand, nobody knows currently what this powerful quantum computers can really, really bring as a result. It's like you have a Formula 1 racing car with 300,000 times more power. Yeah, so you see, the car is not capable to do this power. Bring it in the race. The tires are not capable. The engine, anything. Yeah. So really, this is an exponential and unforeseeable impact. This quantum compute power will have. Last question.
Yeah.
And then my number one global initiative for governance. How do you think this will impact issues of transparency and like symmetry of transparency? We talk a lot about transparency in all possible arrangements that we have here, but then if we have this technology, then what's the use?
Mm-hmm. I'm not really sure if I get it right with transparency. In which area this you're pointing at? Transparency for?
About any activities that one might have in any field. I mean, we're talking about transparency in military things, but also in anything else. Like, we don't know who is doing which economic activity. We don't know who knows what. So trust? What happens with trust? What
Trust,
happens with symmetry? There seems to be this seems to make transparency completely obsolete.
Obsolete.
I don't think so. Yeah. Willst du das?
Nee.
Equity. Equity.
It's a disproportionate
Yeah.
balance.
Yeah.
Okay.
Yeah.
Because of where quantum
So that this technology promotes the one side and the other is losing. Yeah. Yeah. But this is the case.
The availability of quantum and quantum computing
Yeah.
power.
I see.
the
Okay.
Equity is
I see. There, yeah, done. But the quantum compute centers are already available, the qubits, by cloud access. So anyone, can use already qubits. This was not the question?
No, yes, but the thing is, it's people with money, so there's a disproportionate impact.
Okay.
on developing countries.
It's not that costly as you might expect. 1 hour of using a qubit-based cloud compute center, 1 hour of using this is around about €2,000. It's in research, not that much amount of money. Yeah, so you need not to buy the quantum computer and put it in your own data center. Yeah, this costs millions of euros. Yeah, agreed. But the already available quantum compute cloud is really affordable. Yeah.
All right.
Thank you.
I believe we could go on for hours. Unfortunately, our time has run out. Right, Eva? So, yeah. So thank you very much for your attention. If you have questions, have some time, you can still approach our experts and have some bilateral conversations. Thank you.
Thank you. Thank you.